Have you ever wondered why an apple falls from a tree or why you can't push a car as easily as a bicycle? What makes these things happen? Yes, it's forces in physics. Behold the intriguing world of forces, the unseen architects shaping our daily lives. The four fundamental forces, gravity, electromagnetic, strong nuclear, and weak nuclear, each play a unique role that we may not always see but definitely feel. Join us on this thrilling journey as we delve into the world of forces and unravel the mysteries of physics. Before we dive into the fundamental forces, let's talk about a force we encounter daily: the frictional force and the laws that govern all motion. Newton's three laws. The frictional force is the force that opposes the motion of an object. It's why we don't slide around everywhere. It's also why you need to exert more force to push a heavier object than a lighter one. Now, speaking of motion and force, let's talk about Newton's three laws. First, Newton's first law, often called the law of inertia. This law states that an object at rest stays at rest and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This is why your coffee spills when you suddenly stop your car. Your coffee wants to keep moving. Next, Newton's second law, or F equals sign EMA. This law tells us that the force acting on an object is equal to the mass of that object times its acceleration. So, a heavier object requires more force to move than a lighter one. Finally, Newton's third law, often summarized as, for every action, there's an equal and opposite reaction. This law means that any force exerted onto a body will create a force of equal magnitude, but in the opposite direction on the object that exerted the first force. So, the next time you push something or come to a stop, remember it's all Newton's laws and friction at work. First stop, the gravitational force, the force that keeps us grounded, literally. This force is one of the fundamental forces in physics. It's the force that attracts two objects with mass towards each other. Whether it's the moon revolving around the Earth or an apple falling from a tree, gravitational force is at play. Now let's move on to scene 3. The equation that represents gravitational force is F equals m times g, where F stands for force, m for mass, and g for the acceleration due to gravity. This equation tells us that the force of gravity on an object is its mass times the acceleration due to gravity. Unit of force, including the gravitational force, is the Newton, named after the great physicist Sir Isaac Newton, represented by the letter N. Remember, gravitational force isn't just about the Earth pulling us. A universal force that acts between any two objects with mass. The next time you drop something, you know it's the gravitational force at work, pulling it towards the center of the Earth. Now let's invigorate things a little with the electromagnetic force, scene 4. This force is a type of physical interaction that occurs between electrically charged. It's one of the four fundamental forces of physics, and it's absolutely everywhere. The electromagnetic force can be calculated using the equation F equals QE, where F is the force, Q is the charge of the particle, and E is the electric field. The unit of force here is the Newton, named after Sir Isaac Newton himself. This force is incredibly versatile. It's responsible for the way charged particles like electrons and protons interact. When like charges come together, they repel each other, while opposite charges attract. This is the principle behind how magnets work. But there's more. When charges move, they create a magnetic field, and this gives rise to electricity. That's magnets attract and repel, and electricity flows, all thanks to the electromagnetic force in scene 4. Finally, let's dive into the nucleus of an atom where the strong and weak nuclear forces reside. You're at the heart of an atom, amidst protons and neutrons. Here, a powerful force reigns supreme, the strong nuclear force. This force acts like a superglue, holding the protons and neutrons together in the nucleus of an atom, despite the protons' natural tendency to repel each other due to their like charges. The strong nuclear force is so mighty that it overcomes this repulsion and maintains the stability of the nucleus. To measure this force, we use a unit called mega-electron volts, or MeV. Now, scene 5, let's shift our gaze to a force that's slightly more elusive, the weak nuclear force. Unlike the strong nuclear force, the weak nuclear force doesn't bind particles together. Instead, it plays a crucial role in a process called radioactive decay. This is when an unstable atom loses energy by emitting radiation, and it's the weak nuclear force that facilitates this transformation. Just like the strong nuclear force, the weak nuclear force is also measured in MeV. But why are these forces so important? Well, without the strong nuclear force, atoms would fall apart, and matter as we know it wouldn't exist. And without the weak nuclear force, we wouldn't have nuclear fusion, the process that powers the sun and other stars. So remember, it's the strong and weak nuclear forces that keep the atomic world in order, from the stability of atoms to the energy produced in the sun. We've journeyed through the world of forces, but let's quickly recap what we've learned. We started our adventure with gravitational force, the attractive force between any two masses. Remember, it's described by Newton's law of universal gravitation, and its unit is the Newton. Next, we dived into the world of electromagnetism, a force that occurs due to the interaction between electrically charged particles. Its defining equation is Coulomb's law, and it's measured in newtons. Then, we went into scene 6, the strong and weak nuclear forces. The strong nuclear force, the strongest of all forces, keeps the nucleus of an atom intact and is measured in electron volts. On the other hand, the weak nuclear force is responsible for radioactive decay, and also has its units in electron volts. So, there you have it, the forces that shape our world and the universe. Physics is indeed fascinating,